Okay, hi and welcome to the lecture 4.2, so the second lecture of the fourth week of the Domain-Specific Languages of Mathematics course. So first part of this lecture, I will talk about homomorphisms and computing derivatives. So here I've tried to, with my poor handwriting, copy down in a shortened form the funexp type from some earlier live coding. So remember, this is what I called funexp. I will just call f here for brevity. So it's a data type for one argument function expression. So it has a symbolic variable x, which is just syntax for a function id. It has a constant constructor that takes a real number and becomes the constant function, a representation of that. And then you can add and multiply these functions expressions. So this all describes a syntax tree of function expressions, and we have talked earlier about the evaluator, which can translate this function expression into a real function from real to real, a one argument function. And then we were implementing the other day the function deriv, which I here will shorten to der. So it's a function from syntax to syntax. And we already know that derivative is linear, which means that the addition becomes an addition. Derivative of constants is 0, and the derivative of x is just constant 1. And then we showed that we could implement mul d if we give it 4 arguments. But the question here is, can we implement it with just 2 arguments? So with this style of definition that we always call ourselves recursively on the two subtrees, G, F and G. So the syntax tree mul fg has two subtrees, F and G. So intuitively we know we can't do it, but the question is, how do we actually, strictly speaking, prove that there is no ingenious function mul d that could do the trick? So that's what this part of the lecture is about. And first I should say that if der is free to do whatever it wishes, then of course we can implement mul d. In fact, any function with the right type will be an implementation of mul d. It just will not have the desired properties. So what is the desired properties? So I'm trying to see here in quotes that der should implement the mathematical derivative of one argument functions, and we will make that more clear on the next few slides. So the full logical statement that we'll set out to actually disprove in the next few slides, that is, there exists any function mul d such that der is a homomorphism in 2 arguments from multiplication in the syntax tree to some unknown operator on functions at the same time as der actually implements derivative. Okay, let's move on. Here I'm trying to clarify the types a bit. So I've first given a little diagram here in the middle. So the diagram says that the type of der is f to f, so funexp to funexp. It also says that normal derivative is s to s, where s is actually r to r. So real number, one argument real functions. So notice that this is a higher order function, d. It takes a function and returns a function. Okay, and as I mentioned earlier, we can evaluate a syntax tree to a function, and that's the function eval, which we've used before. And we know that eval is a homomorphism. So here is the same eval applied on the result side. And this is a so-called category theoretical diagram, and we can go through this diagram by function composition. So if you first apply the derivative, we get a syntax tree which we can evaluate to a function, or we can first evaluate it to a function and then compute the mathematical definition of derivative. If we take this root, the underlying down root, we can't do it in Haskell, but if we do the upper root, we can. Okay, and what does the specification that there implements D, what does that mean? Well, it means this expression on the right side up here. So it means that both ways of going around this little square gives the same result. So if we first evaluate f and then take the mathematical derivative, we should get the same result as first taking the syntactic derivative and then evaluating. And this should hold not just for some f, but for all syntax trees in this data type f. And I've underlined both the left-hand side and the right-hand side in yellow, and I've indicated in the figure a yellow arrow between the syntax tree and the semantics. So you can see that the type of this diagonal is actually the same as the type of the evaluator. So the evaluator translates from an F to an S, and also this diagonal or this composition computes from a syntax tree a normal mathematical function of one argument. Okay, so this expression for all f, d after eval is the same as eval after dev. That can also be written as a homomorphism. So here I've summarized it below as a one-argument homomorphism, that eval transports syntactic derivative to semantic derivative. And this is not a magic trick that I'm doing here. It's just I see the pattern that you see I push the eval function inside there, and then it becomes d. And that's exactly what the definition of H1 is doing. H1 says for all f, d of eval of f should be eval of der of f. Okay, so I have a short and concise and formal definition then of what der implements d means, which I will use later. Okay, now if we think back, we remember that we had an example which was a counterexample to a homomorphism, and that example was is prime. So if we look at the lower half here first, so the is prime, then we said we had x and y equals 2, and then we had, which I call here an x bar, which was 3. And we knew that the primeness of x and x bar was the same, but if we would add x and y, or add x bar plus y, then we would get different primeness. This is 4, so is prime of 4 is false, but is prime of 5 is true. So even though is prime of x equals is prime of x bar, we don't have that equality after we add y to it. And this means, down in the left corner, that we get a bit of an interesting chain here. So is prime of x plus y is prime of x. If we assume there is an operator to a homomorphism to this operator, is prime of x and is prime of y. And we know that this expression, these two expressions are the same. But we also know that the result, because we evaluated here on 4 and 5, are not the same. So we have this circle of equalities, which here says equal, 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 and then not equal. So this is clearly a contradiction. So we want to copy that setup here. And to do that, we would like to assume that there exists a mul d with this property, the H1 property. And we want to find some arguments f, f bar, and g, such we can do a similar argument as for the is prime case. Okay, so here I just summarize what I said. Can we find the f bar, and the g such that the derivative of f is the same as the derivative of f bar? So they can be different syntactically, the f and f bar, but the derivative should be syntactically equal. But yet we should have such that when we multiply those by g, the two different f and f bar, then the derivatives would be different. And yes, it's not very difficult to find such examples. So I'll just move rather quickly to this case. Informally, we have the computation here. And let's choose f and f bar to be x plus 0 and x plus 1. And here I said informally, I use these quotes to sort of use a simplified syntax for the expressions. I mean, f times g, where this is x plus 0, which is just x, and g is x, that is just x squared. And the derivative of x squared is just 2 times x. But f bar, which is x plus 1, if I multiply that by g, which is x, we get x squared plus x, whose derivative is 2x plus 1. So this clearly seems to be difficult to satisfy at the same time. I mean, these two expressions are not the same. But this is a little bit of hand waving. We got these quotes, we got this x, which is unbound, and so on. So let's see if we can make this completely formal in the next few slides. So I should note that the expressions here may look a bit contrived, but they are chosen so that we can actually get exactly syntactic equality between derivatives, so that we are really mimicking the case for the S prime. Okay, so first then, we have candidates f and f bar, and let's see if we've actually computed, if the derivatives are actually the same. So if we compute the derivative of f, we had a few slides back the definition. It went down recursively, it just gave back the same add constructor. Then it took the derivative of x, which was const 1, and then it took the derivative of const c for any c, and that was const 0. So both f bar and f have this as the derivative. So you could say that this can be simplified to just const 1, but strictly speaking, the syntax trees don't have a built-in simplification. We could make a derivative function which has built-in simplification, but that's not the case we're trying to prove here. Anyway, so both these two, computing the syntactic derivative of f and f bar gives exactly the same result. Add const 1, const 0. And we also have an informal hunch that the derivative should be different, or the multiplication should be different. Okay, let's move on. And why I say informal hunch is because the derivative of the multiplication case depends on mul d, which is completely free here. We're just asking ourselves, does there exist any definition of mul d? The only thing we know about it is its type, and the fact that these properties should hold. We don't know what it would return in the multiplication case. It doesn't have to do any kind of multiplication. It can return any term it wants, and we will still prove that it cannot exist. Okay, here comes a rather open slide, which is the main computation for this proof. So I've copied the information we have. We have sort of the three values, f, f bar, and g, and the fact that both their two derivatives are identically add c1, c0. Now let's do a computation which should end in the contradiction. If we get a contradiction, then all is fine. We managed to disprove the existence of mul d with these constraints. Okay, so first I will define two functions, age and age bar. So age is, well, actually it's syntax trees, so it's the application of der to mul f g. So we don't know the end result, but we know that we've assumed it has a function mul d, so this should be mul d of der f and der g. So let's stop there for the moment. Let's also define h bar with a little space in between. So h bar is the derivative of mul f bar and g. And also, we have assumed this is a homomorphism. So it is mul d of derivative f bar and derivative of g. And then we can see that both from the below and from above, these are both equal to a common term, which is mul d of, and then look what we've got up here. I'll just write a little arrow, a blue arrow. This expression. And for the other case, derivative of g, that's just const 1. So notice this intermediate term here is equal to both h bar and to h. And that's because we know that der f is equal to this expression, the blue one we filled in, and also der f bar is equal to that. So even though we don't know what mul d is doing as a function, it could return whatever syntax tree it wants. We know that there is one specific syntax tree it returns. We can even give it a name. Let's call it k. So this is just an equality chain. So h equals k, which equals h bar. So h and h bar, according to these assumptions, are the same syntax tree. So now we will try to go towards the impossible part of the contradiction. So the only remaining information we got is the specification. The specification used eval. So then we have to form an expression of eval, and we can do it in two different ways. We can write eval of h, and we can write eval of h bar. So let's start with eval of h. So eval of h, I'm just writing out the definition of eval. Sorry, not definition, eval of h. So it's eval of der of mul f g. So this was just copying down this line here. Okay, now I'm using the specification. So the specification, remember, said that eval is a homomorphism with respect to der. So it takes the syntactic derivative to a semantic derivative. So this means that this is also equal to the semantic derivative when we've moved the evaluator one step inwards. So I should perhaps mark here with the color, say blue, that this case here is motivated by the specification. I can write it here and then we probably have to erase it to fit in. That was h1. Oops, sorry, I had a smaller one. h1, it was saying that eval satisfied going from syntactic derivative to semantic derivative. Okay, anyway, the reason I'm doing the transformation into the mathematical world is then we can start computing the derivatives. So first we have to compute the eval for the multiplication case. And we know that if we remember that we introduced instances of multiplication for functions, we might remember that eval is also homomorphism. So we can keep the derivative on the outside and say that this is actually the same as eval of f multiplied by eval of g. And here again I can make a little note that the multiplication here is the multiplication for functions. So it's pointwise multiplications of two functions. F and g are syntax trees, but eval f and eval g are normal real-to-real functions. Okay, and not only are they functions, we also know what they compute for. 2. So if we look up here, we know the syntax tree for f, and we know the definition of eval from last lecture. So eval of f is the sum of the eval of x and the eval of const 0. So that's just eval of x is the identity function, and this is the constant function. So semantically, this is equal to still the derivative of the identity function, and actually times the identity function. Okay, so derivative of the identity times the identity, that's the same if you want to recognize it as the derivative of the function that takes x to x squared. Remember, the identity function just returns its input, and there is multiplication between the two x's. And we may remember that derivative of x squared is the function, well, actually there's no derivative left, we can compute the derivative, so we can even write it here. It's just 2 times. Okay, so what we've computed here is that if we evaluate age, we will get the function that multiplies its argument by 2. Okay, let's evaluate age bar. So we know from above that it's equal to age, but that's not deter us from that. Let's use the specification or the definition of age bar here. So we just again write eval and splice in there of, in this case, a different expression, mul f bar and g. But otherwise, we can use the specification, the same specification here. And the specification is saying that eval after der is d after eval. So we can push eval inwards to this position. And otherwise, the expression remains the same, mul f bar g. And using the same law as above, it's the derivative of eval of f bar times eval of g. And again, something very similar comes out, but now f bar, the eval of f bar, is not the identity function, it's the identity function plus 1. So we have still the d outside, and then we have the function x to x plus 1 times id. And if we want to simplify that a bit, that's the derivative of the function lambda x to x squared plus x. And we know what that derivative is. It's the function that takes x to 2 times x plus 1. Okay, so we have used the specification of eval and rules for derivatives, and we've computed the eval of age and the eval of age bar. Okay, these two, I mean, age is equal to age bar. We know that from above here. They are both equal to some case, some k. We don't know what syntax tree it is, but clearly it's an equality chain here from age to k to age bar. So whatever syntax tree they are, the evaluation of that syntax tree is some concrete function. It's the same function in both cases. So that means that we have proven here that eval, I should write it, eval of age applied to any x is equal to eval to age bar to any x. Because if age is equal to age bar, then certainly if we evaluate it, we should get the same. Well, this means that the 2 times function applied to x, so 2 times x, I don't even need the parentheses. I'm just using here that we know that eval age is the 2 times functions, and if we apply eval age to x, then this is just 2 times x on the left-hand side, and on the right-hand side, it's this other function applied to x, so that's 2x plus 1. And now let's subtract 2 times x on both sides. So then we have proven that 0 equals 1. Okay, 0 equals 1 is clearly a contradiction. So by assuming that there exists any mul d without requiring anything of its result other than that for every concrete pair of arguments it's some kind of syntax tree, and the specification that eval should implement, that der should implement derivative d, that assumption is falsified by showing that this assumption leads to a contradiction. So if we sum this up, yeah, this was just the previous, I computed it beforehand. We summed up the assumption we had from the beginning. The question, does there exist a mul d? So the answer is no. There doesn't exist any mul d such that these two things hold at the same time. So the syntactic computation of a derivative, which we have defined, it is a function, but it is not a homomorphism. Okay, I know that this definition, this little part of the lecture was rather abstract, so let's make a break here and then we'll continue with some more examples afterwards.